Patrick, and we're here to talk Drives 101 today. This is some basics of AC drives. Just to begin with, a couple of reasons you might want an AC drive. If you take a standard AC motor and connect it across the line, it's going to run at its nameplate frequency. In the United States, it's going to be on a 60 hertz line, and if it's a 4-pole motor, it's going to run at 1800 RPM minus some slip, so maybe 1750 would be a very typical number. If it's a 2-pole motor, it's going to run about 3600 RPM minus slip, so maybe 3500 RPM is all you're going to get. If it's an 8-pole motor, it's going to run 900 minus slip. But it's not adjustable within those ranges. So if you want to adjust the speed of an AC motor, you need an AC drive. A couple reasons you might want to control the speed of an AC motor. One of them is the process just simply requires it. If you think about a winder-unwinder application where you have a big cylinder of rolled material like a steel metal sheet, and you're trying to unwind that and maybe slice it up into pieces, you would need to take it off of an unwinder coil, and the farther you get toward the end of the coil, the faster that motor is going to have to spin, if you think about it, to keep the same linear speed going on that sheet. Likewise, correspondingly, on a winder application, the motor is going to have to go slower and slower as the reel gets larger and larger to compensate for maintaining a linear speed. Another reason you might want an AC drive is for energy savings. Pumps and fans, or what we call centrifugal loads, present the potential for energy savings. And the slower you can run them and still accomplish the purpose you had, the more energy you can save. A few basics about how an AC drive works. In an AC drive, we take the AC line, we send it through what we call a DC bridge, and we create a DC bus. And that bus then, the bus voltage level is kind of governed by the level you put in over here. So if you put 460 volts in on the AC side, you're going to get a DC bus in the 650, 700 volt range. Here's the input 3-phase AC signal. After it goes through the diode bridge here, it looks kind of like this. It's got a bunch of lumps in it. It's kind of DC, but it's kind of noisy. It's got a bunch of ripple, we call it. Then we put it through a capacitor bank, and that capacitor bank has the effect of stabilizing that voltage and giving us a very solid DC level to work from. So what do? Now we turned AC into DC. What do you think we're going to do? We're going to turn it back into AC. So the output stage here, these 9 transistors, which are called IGBTs, or stands for insulated gate bipolar transistor, these are switches that can turn on and off. And when you turn on and off these switches, you create kind of AC. What you really create is a bunch of pulses on the output that are either positive or negative in nature. You can see these are positive pulses, these are negative pulses. And then we can vary the width of those pulses in something we call pulse width modulation to create a simulated sine wave. And when that voltage, that PWM voltage signal gets run through a standard AC motor, we get a wave that's a little noisy, but it looks a lot like a sine wave. And now, though, we have the ability to vary the frequency because this output stage is controlled by a microprocessor, and it can respond to whatever commanded frequency we give it and run at that level. AC drive control strategies. There are several different ways that you can control an AC drive. If you go back in time, the original AC drives were what we call volts per hertz or scalar AC drives. And what that literally meant is that the voltage was always a ratio of the frequency we were outputting. So if it was a 460 volt, 60 hertz motor, and we tell the drive to run at 60 hertz, it's going to output 460 volts. If we tell the drive to run half speed, or 30 hertz, it's going to run 230 volts. And that ratio is always going to be maintained. So in an open loop scalar or volts per hertz drive, that's what you get. You get a constant volts per hertz ratio. The next thing that kind of came around on the horizon was closed loop vector control. In this case, we connect an encoder to the motor, and the encoder generates pulses back to the drive. The drive can count those pulses and determine how fast that motor is going. Why is that important? Well, it's important because we talked about the motor's slip here. The more heavily you load the motor, the more slip will occur in a standard AC induction motor. So the encoder can measure the actual speed. It can say, no, you only think you're going 900 RPM. You're actually going 850. And then the drive can respond to that and crank it back up to the 900 RPM level and adjust for that slip. So encoders allow you to control the speed very, very accurately in a vector drive. And there's a couple types of vector control. There's closed loop vector, very, very common type of control. What we do here is we got the drive here. This is the diodes we talked about in the IGBT output section we talked about. We have an encoder on the motor, and that encoder is brought back into the drive through the microprocessor, and the encoder sends pulses out. So the drive can look at those pulses, and it can determine how fast the motor's going, how fast it's really going. Now, why is that important? Well, it's important because I said you could run half speed and at half the voltage, right? And you'd say, well, that should be half speed. Well, we got this thing I talked about earlier called slip, which is a problem because the heavier the load, the more the slip. So I can think I'm running half speed, which would be maybe 900 RPM, and I'm really only running 850. Well, some applications wouldn't care. If I'm running a fan, it probably isn't that critical. But if I'm running a conveyor line, I might need to know more exactly how fast I'm going so that I don't drop boxes off the end or not get them to where they're supposed to go. So this can tell the drive exactly how fast that motor is going, and then the drive can adjust to say, oh, I'm supposed to be at 900, I'm at 850, I better bump it up a little bit. So that's built in. So that was the first evolution. And then some very clever engineers decided that they could do it without the encoder. They put in these current sensors that all they do is measure the current going out to the motor. And they maintain in the drive what's called a model of the motor. And usually for this type of control, there's a tuning algorithm that happens where when you first initially connect the drive to the motor, you tell the drive, I want you to go learn everything it can about that motor. And it runs through a tuning algorithm. It'll lock the rotor for a while, then it'll run it up to full speed, and it'll decelerate it down, and it might do it again. And it tries to measure the characteristics of that motor and log those parameters into its memory. Now it knows about the motor, and it can now estimate the speed more accurately. So that's what both open loop centralist and DTC centralist control do. Now, DTC centralist control is ABB's proprietary centralist vector control, and it kind of goes a step farther. And it's a pretty complex conversation, but just to make it in a nutshell, what it does for most people is that you can get 100% torque at zero speed with this type of control without an encoder. So if you have a motor and it's got a rated torque value and you have a need to literally have 100% torque all the way down to zero for your application, you can do that. Things like paper lines come into your mind when you think about that kind of thing, where you really have to have excellent control of the torque or you're going to break the web. Okay. Now we got our drive, we got our DC bus, we got a way to recreate the AC, and we got some control techniques. Now we need to talk about the types of loads that are out there. There's really two types of loads that are out there. There's constant torque and variable torque loads. Constant torque loads, the torque required out of the motor in this application is the same. It's constant over the speed range of the application. So a conveyor is a good example of this. If I have a loaded conveyor sitting there and it's just loaded up and I start it, it's going to take the same amount of torque to start it right from at zero speed, at 10% speed, as it is at 100% speed. So it's going to take constant torque. So in a constant torque application, as I drop off the speed, my horsepower drops, but my torque remains the same. That make sense? The other type of load is a variable torque load. These are things like centrifugal pumps and fans, and these happen to be about 70% of the applications out there. So pumps and fans are really common on drives. And what you get here is the torque falls off kind of on this first curve line here. And that's called, it's a quadratic curve. It's a square factor. So as you drop in speed, you get down here to half speed, I'm at 25% torque. That's really characteristic of a pump, or most pumps and fans out there. Especially if they're centrifugal, it is characteristic of it. There are some other pumps that maybe you've heard of, positive displacement pumps. They don't work that way. But centrifugal pumps and fans do. Now, the interesting thing about this is that what happens next is we take a look at the actual power required. The power follows this curve, this darker line here. Power falls at a cubic rate. So here's the real energy saving advantage with the drive. If you can, in your application on a variable torque load, slow it down any bit at all, you're going to save energy. If it'll still do the job you want, slowed down, it will consume a lot less energy. And for example, if you can run even 20% less speed than what's full speed, you're going to consume about half the energy. Because if you take the reason that works is if you take a half and you cube it, you get an eighth. Excuse me, say that again. You take 0.2 and you square it, it's going to come out about 81% speed. It's going to be about half energy. That, I guess what I was trying to say there is you could also, if you could run half speed, then you can really save a ton of energy. And that ends up being an eighth, because a half cubed is an eighth. But that's probably, you can't run at half speed. Probably that's not realistic. But there is considerable energy to be saved simply by slowing it down any amount you can. Most variable torque systems are designed for worst case scenarios. They have to be. If you think about an HVAC type application, it's got to be designed for the hottest day of the year. Nobody wants to be hot on the hottest day of the year. So the system's got to be big enough to do that. And then they probably put on a safety margin, right? Because it's getting warmer every day. So there's probably a safety margin built in there too, so that the air conditioning system can always deliver more. If you can run it up to full speed and then back it down any, we're going to save energy, like we said. Now the other thing is that their system demand changes. A lot of times these systems don't run on weekends. They don't run at night, right? They save the energy then by shutting off. So their duty cycle is even less. So what the bottom line takeaway is that few systems require 100% flow out of a pump or fan continuously. They might require 100% flow a couple times, but they don't require it very often. These three charts look complicated, but they're really simple. They're called the affinity laws. Each one of them is got on the bottom axis the speed you want to run in percent speed, from 0% speed to 100% speed. And on the other axis, there are three different variables. On this one, there's flow. So if this is a pump, and if I start at 100% speed and I slow it down to 50% speed, I get 50% of the flow out of that pump. Straightforward, linear relationship. The head on the output of the pump, the pressure, what they call the head, is a curvature. It's a squared relationship. And then the input power to the drive is this cubic relationship. So it's the same energy saving criteria we were talking about before. This is how we can save energy by slowing down a pump or a fan. And these are some of the charts we were talking about before. Remember I said if you could run 80% speed, you use about half the energy. If you can run 70% speed, you use about a third of the energy. So if you can slow it down and still do the job, you conserve a lot of energy. So this is the takeaway bullet. Centrifugal loads, pumps and fans offer the greatest energy savings when you can run less than 100% flow. That's the bottom line. So here's an example. Here's a 100 horsepower motor. It's an induction motor. It's got slip. If it runs at 100% speed and 100% load, so it's always 100%, and it's a 95% efficient motor, just to pull a number, and we run it, and our cost of energy is 8 cents a kilowatt hour, and we run it 12 hours a day for 360 days a year, we're going to burn $27,000 worth of energy. If we can run that same motor at 60% speed, and we slow it down to 60% of its normal speed, the equivalent horsepower is 22%, and if you could run at that all the time, which you probably can't, but if you could, you'd use $59.70 a year. Now that means you could run at 60% speed all the time, and that's probably not realistic. but it might be realistic 3/4 of the time. So in the best case scenario in this application I just gave you, you could save $21,000. That's probably not realistic because we said sometimes you do have to run faster. But if you go back here and say, okay, maybe I only have to run 100% of the time, a couple days a year, maybe I can still save $15,000. It's a big number. You understand? Okay, so that's kind of the energy savings take on why you would use an AC drive. On variable torque loads, you can save a lot of energy and a lot of money. Some other common characteristics of AC drives. Digital inputs, digital and analog inputs. Now we got this drive sitting there, and it can make PWM, it can rectify the AC into DC, and it can make PWM. We have to have some way to control it. How do we do that? Well, we have what's called DIs, digital inputs, and AIs, analog inputs. And what we do is, this particular drive has 6 digital inputs and 3 analog inputs. That's what it's got. DI1 is set up for start-stop. What does that mean? That means if I connect the 24-volt supply out of the drive through a switch to this DI1 input, and then I close that switch, the drive will start. Well, how fast will it go? It'll go the speed that I put into analog input 1. Well, what does that mean? Well, I have here, this one happens to be run off a potentiometer. So I have a 10-volt reference level here on pin 1, and I have a ground on pin 2, and I run those into the pins 1 and 3 on the potentiometer. And then I run the middle, the wiper arm, into the analog input. So this analog input now can vary between ground, or 0 volts, and the reference of 10 volts. So, what does that mean? That means that when I dial the potentiometer all the way to 0 volts, the drive's going to stop. If I drive the potentiometer all the way up to full speed, it's going to run 1,800 RPMs. If I put it in the middle, it's going to run 900 RPMs. I have a way to control the drive. Now, this example here shows a potentiometer for that control, but that could just as easily be a PLC, a building automation system, anything that can give you a voltage signal, 0 to 10 volt voltage signal. There are other controlling inputs for a drive. We have something called constant speeds. Some manufacturers call it preset speeds. All that means is that I take a couple digital inputs, a couple or more digital inputs, and I can define the speed at which that drive is going to run. I do it by preset speeds. So I go into my drive and I say, okay, constant speed 1, that's going to be 900 RPMs. Constant speed 2 is going to be 1,000 RPM. Constant speed 3 is going to be 1,500 RPM. And I program those in there. And then when I come in and I turn on the start command, and then I turn on DI1, it will go to 900 RPM. If I turn off DI1 and I turn on DI2, it'll go to 1,000 RPM. And if I turn them both on, it'll go to that 1,500 RPM. And those numbers I made up, the 900, the 1,000, and 1,500, you can program those to whatever you want within the speed limits of the motor. This particular table down here shows a 15-speed preset speed that you can do with 4 digital inputs. If all those digital inputs are off, the drive runs underneath the analog input. It runs under that normal analog control. But if you turn on the first digital input, it'll go to constant speed 1. You turn on the second one and turn off the first one, it'll go to constant speed 2. Ends up there's 15 combinations here. Have them all on, it'll go to constant speed 15. So if you have an application where you really just need to go to very preset levels and you always want to go to those levels, a couple digital inputs will do that for you. Now, there's a couple types of controls. Drives are commonly used to replace motor starters. The example I showed you on the 2 slides ago where I talked about the DI1 switch to start and stop the drive, that's called 2-wire control. Very simply, I hook the one side of the switch up to 24 volts, and I hook the other side of the switch up to DI1, or whichever digital input I want to use. And if I close this switch, the drive starts, and if I open this switch, the drive stops. 2-wire control. There's literally 2 wires on that switch that are involved. That's why it's called 2-wire control. If you were replacing a electromechanical starter, a lot of times that comes in a little starter combo box, and it's got a start and a stop push button on it. Start black and the stop is red. Typically that's how they're set up. Well, we can do that with the drive too. It takes two digital inputs, so in this case we're going to do it with DI1 and DI2. And the way those push buttons work is that the start input is a normally open contact. What does that mean? Well, it means that the contact is held open by a spring. It's like this. Normally it's not conducting at all. When I push the button, it makes that contact, and then when I release the button, it opens that contact. It's normally open. This one, the stop button, the other button, is a normally closed button. And the spring holds the contacts together. I push in the stop button and it opens this contact. When I release it, it recloses it. Okay, why is this important? Well, I press the stop button. I press the start button rather, and what happens is the drive says, okay, DI1's closed, DI2's closed. That means start. Once it gets that signal, it knows to latch that. And even when you open this, it'll still keep running. So it latches in the start command. DI2's is the stop button. If it ever sees DI2 open, it will stop the drive. It'll bring the drive down to this deceleration ramp and stop it. A lot of times, interlock contacts are brought in here into the stop command so that the drive will stop if any kind of safety switch is open. That's why they're always normally closed. And the reason that stop buttons are really normally closed is this simple. If a wire falls off, the drive is going to stop. Any kind of loose wire, somebody yanks on a cable, it's going to stop. That's safe. If the drive kept going when somebody pulled a wire off the stop button and I couldn't stop it, that would be a problem. So the reason the stop button's normally closed is for safety. Run enable. A lot of drives have what's called a run enable signal. This is, in addition to the start commands and the stop commands that we talked about, this is a signal, and this one you can see this on this particular drive, it's brought into digital input 6. If I open that contact, if I open up this DI6 switch, the drive's going to not only stop, it's going to stop gating. It's going to stop providing energy to the motor. Now there's a difference there. Back here, when we talked about a stop command, the drive, when you open that switch, it can ramp to stop, which means that you can bring it down on a controlled ramp at whatever rate you want. If you want it to take 30 seconds to stop, that's fine. If that's, maybe that avoids some mechanical stresses on your system by having a long ramp rate. However, this run enable signal here, if you open that, it's going to stop energizing the drive. There's going to be no more voltage going out to the motor. So it stops electrically providing energy to the motor, and the motor's going to freewheel. So it's not going to stop as fast as if it were on a ramp stop, but it will stop providing energy, electrical energy to the output. And so that's another kind of safety issue. There's a couple different start modes available to us. We have a normal start mode that'll happen if you just plug in the drive and auto-tune it and start going. But sometimes there's a need to catch a motor that's already rotating. For example, if you have an application on a fan where that motor can what we call windmill, the airstream can literally make the motor turn when we're not there, when the drive's not even running. That can be a problem for a drive if it thinks that motor stopped and it's not. And what will happen is it'll yank it down to 0 speed and try to accelerate it. And it might or it might not be able to do it. That's point one. And it might trip if it tries to do it. So it might cause a fault. So what we do, if we know we're going to have that kind of situation, we tell the drive to use a flying start mode. And what it does is it sends a small amount of electrical current out to the motor, and it watches the current coming back on those limbs, on those current detectors, and it kind of estimates where the drive is based on the current signature of that motor. And it's kind of searching for that speed. And when it finds it, it locks in, and say it's going half speed. It'll start at full speed, and it'll kind of ramp down until it finds it. Once it finds it, it'll accelerate it back up to speed. So it's a way to catch a flying load. If you ever heard of flying start or catch on the fly, that's what that term means, to catch a rotating motor. There's also a way if you need a lot of torque to break something away. If you have a very high stiction application where maybe you got a heavily loaded rock conveyor and you got to get it started, right? You can pre-magnetize the motor with what's called a DC magnetization. You can kind of prime it, if you will. And then when you hit it with the start command, it's going to have all possible torque, and it's probably going to break free that load. But this is usually a separate input that does this. So you might have an input to say DC magnetization and then an input to say start, or it might be that it does it based on time. You might say, I want you to DC magnetize for 2 seconds and then start. Okay, and that's a little experimental. As you set up the drive, if you've got this type of load, you have to experiment with those parameters to find the right point. Starting modes, there is in most drives the ability to have what's called torque boost. And what you get is, if it's a hard to break away load, there's another way you can do it. You can, normally this is the volts per hertz curve. It goes up on this curve where your voltage and your motor speed are 1 and 1. Well, you can also increase the motor first higher at low frequencies to give that more torque to break away, and then bring it back into the normal ramp. So if you have a load you can't get started, a lot of times we'll say go crank up your V-boost a little bit and see if we can get it to start. Other things drives have, ramps, and we kind of mentioned this briefly. There's actually a separate ramp for XL and a separate ramp for decel. So you can program in the time it takes to get from 0 to full speed. Now, that literally specifies a rate when you think about it. If I say my motor's going to go from 0 to 1800, and I put 60 seconds into XL, that means it's going to take 60 seconds to go from 0 to 1800. If I only want it to go to 900, how long is it going to take? It's not going to take 60 seconds, it's going to take 30 seconds, right? So the XL time is specified as the amount of time it takes to go from 0 to full speed. Or rated speed, I should say, rated speed. Decel is the same way. That's how long you want to take it to go from full speed down to 0. In addition, there's 2 sets of ramps. There's ramp XL1 and XL2 and Decel1 and Decel2. You can select which ramp you're going to use based on what you want to do. Sometimes you might need a faster ramp and sometimes a slower ramp. You can control that with these 2 ramp rates, and you can have a digital input that controls when one is active or when the other one is active. Maybe sometimes you got a lightly loaded system and you want to go real quick, and other times it's heavily loaded and you want to go real slow, for example. You can also control the ramp shape. This is a linear ramp. It goes flat out from 0 to full speed on a straight line. You can also have a S-curve ramp. An S-curve ramp starts a little slower, joins the normal ramp rate, and then at the top it gets slower again, so that if you have a high inertial load that you really get spinning quickly and you just keep running up there, you're really likely going to overshoot your speed. And that might be a problem for your application. So you can, when you get close to the running point, you can level it out, not accelerate so quickly so that load doesn't overshoot and doesn't go too fast. We've got something called slip compensation, which is available in volts per hertz drives. This applies to volts per hertz or scalar drives only. And what it does is it looks for a amount of slip, and it's in terms of percent. So if you know that the drive is a 1750 RPM motor and you want to run 1800, that means the slip is 50 RPMs at full speed. You can take 50 over 1800, get a percentage number, and put that percentage number into this parameter, and then the drive will always run that percent extra on the frequency, so that when you say I want to run 900, you really get something pretty close to 900. You don't get 800. Okay? So it's a slip compensation. There's some DC capabilities in a drive. AC drive, but it can output DC. It can output DC because we got a DC bus there. If we want DC, all we really got to do is close the switches right. So we can put DC on the motor, on 2 legs of the motor. And what that will do is that'll have the effect of holding the motor. We can implement what's called a DC hold function. And DC hold means that motor's ramping down here. We told it to stop. It ramps down to this DC hold point, and then it just injects DC out there. So the motor will hold. It'll hold at that frequency. And then if we're ready to run again, when we issue our run command, it'll stop the DC injection and it'll go right on out and run again. So it will output DC to the motor whenever you're not commanding a speed. All right? DC braking is a little bit different in that it's a type of braking. It's the same idea. You're still outputting DC to the motor, but you do it at a point in the deceleration ramp, and it will help bring the motor down quicker. Okay? We're going to talk a little more about braking here later, so I'll leave that at that for now. There are some parameters associated with this. The DC hold speed, that's the point at which you want it to change over from AC to DC. How slow do you want it to be going when you tell it to hold that motor? You want that to be 100 RPMs, you want it to be 10 RPMs. What do you want it to be? The current reference, that's how much DC you want it to give. That's kind of trial and error. You don't want to put any more DC out there than you have to because it can go hard on the motor. But you have to have enough to hold it. So depending on what you're doing, you have to play with this reference parameter here and get the right reference, the right percentage current. And then this is the DC brake time. This has to do with the DC injection here in the slide before. Back here. Here, when we start injecting DC, how long do we want it to inject DC for? That's a parameter we can set. Braking is needed in some applications. Sometimes you have something that you need to help braking with. It takes too long to stop by itself, so you need to have some help getting it to brake to a stop. When does this happen? A lot of times it's with safety, right? Maybe you've got a circular saw on a table saw and you got to drive on it, and you need it to stop running as soon as you tell the drive stop. Now, the thing is, if you had a motor starter on that and you just simply turn off the power, that thing's going to freewheel all day long, all right? And it's going to take minutes to come down. There's going to be a rotating hazard there. If you use braking, you can take even a large saw blade and decelerate it quickly through some of these braking techniques. And the drive has actually got multiple braking techniques. So there's also the ability for the drive to take an overhauling load and brake it. That means something that's got a high inertia, like a flywheel. Flywheels will spin for a long, long time, a big flywheel will. So you can take the energy out of the flywheel, put it back in the drive, and use that to slow down the motor quicker. And depending on how fast you want it to slow down might determine what type of braking we have to use. Here's our motor. If this is an overhauling load and we want to stop it quickly, that energy is going to come back through the output stage here, and it's going to come back through these transistors because there's something called a flyback diode around these transistors that lets the energy from the motor come back in. Now it comes back in to the DC bus. It can't go any farther because these are diodes and they're turning the other way. So what's going to happen when you decelerate this motor, this bus voltage, the DC bus voltage, is going to go up. And it can only go up so far before we start having issues with damage to some of our semiconductor devices here. So we have a limit here that we can go to, but we can definitely slow things down. If we get over those limits, there's some things we can do. There's some ways we can get rid of that energy. 5 types of braking here. First off, there's mechanical braking. This is the most straightforward braking. There's a brake on the motor. All you have to do is tell that brake when to engage, and it'll stop the motor, and the drive doesn't have to do anything, right? And all that energy goes into heat on the brake pads. So that's a simple one, just like your car. No problem there. The drive has actually control logic to sequence on and off that braking contactor. So you could hook it up to some of the digital outputs on the drive and control the mechanical brake on the motor. But if the motor doesn't have a brake, there's still some options. DC injection. If you put DC onto an AC motor, it will cause braking torque. That depends on how fast you're going as to how effective that braking torque is, but it will cause braking torque. There's also a method of braking called flux braking. This is a sort of unique control algorithm that's available on ABB's DTC drives. Not all drives have flux braking. And what it lets you do, it's most effective on small motors here. See, like 2.2 kW is about a 3 horsepower motor. And you can see the amount of braking torque you get. As you get slower and slower, you get more and more braking torque. And what it really is doing is it's putting the it's using the motor slip to create braking. And it's using the DTT control algorithm to do that. And like I said, it's most effective on small motors. Now, if that isn't enough, we have something called dynamic braking. So I mentioned before that as we regenerate, as the motor is overhauling and trying to slow down, we're putting energy into the capacitor bank. We're putting it on the DC bus. That DC bus voltage is going to go up. It can only go up so high, or the drive will say, time out, I quit, trip, and the motor, we lost control of the motor. And we might have got it slowed down a little bit, but now it's spinning again, and we didn't get it stopped. And the bus can usually go up to 800, 850 volts, and that's about it on a typical 460-volt drive. So that might work for some applications, depending on how fast you're trying to stop. For others, it won't. What we do is we have an ability on our drives to connect up what's called a braking resistor. And we connect it up to a switch, another transistor. It's called the 7th switch, 7th IGBT, that gates on and off and takes the energy out of the DC bus and throws it into the resistor. So now, as you're decelerating that load, the energy is going into the drive, and then it's going into the resistor and getting burned up in the form of heat. Another way to stop the drive. And a relatively inexpensive way if you need to stop a load quickly. Resistors are not that expensive. Yet another method, we have what are called regen drives. What does that mean? That means that this drive is essentially two drives in one. It's got a drive that will drive the motor. It's got a drive that will drive back to the line. So if we start pulling energy out of the motor, if you look at this diagram here, out of the motor and back into the DC bus, and we detect that the DC bus has gotten high, this section is replaced with another drive that goes back to the AC line. And it starts making AC at 60 hertz, and it syncs it up to the line, and it starts putting energy back onto the line. So now we've got, with a more expensive drive, and when you think about it, this is almost like two drives in one, so it's a little bit more expensive option. But what it does is it puts the energy out of the motor when you decelerate back on your grid, and you can use it somewhere else or to drive something else. There's energy savings in the regenerative process. This happens to be a test stand for a car. One of the great applications for regeneration. You know, as this engine in the car drives the test stand, it's literally putting energy back into the test stand, and that energy's got to go somewhere. And this is a perfect example for where it should go back to the line. Now, I mentioned before braking on a car and how that's kind of like a mechanical braking. If you think about some of the hybrids out there, they got this huge battery bank. Well, literally, there's an example of a drive where when you go down a hill and you want to slow down, you take your foot off the gas, it's going to take that energy that from gravity that's pulling through that motor, and it's going to put it back into the battery. And that's how hybrid vehicles partially recharge their batteries. They still have to be, there's losses, they still have to be charged at home and all that, or electric vehicles, or you have to burn some gas on a hybrid. But the batteries themselves are recharged partially by every deceleration, by every hill you go down. You think about it, anytime you take your foot off the gas and you're going down a hill, you're putting energy back into the system. Well, thank you everybody for your time. I hope you found it educational.